Hello, in this module we will introduce the cumulative distribution function, also called probability distribution function, abbreviated as CDF or PDF. The abbreviation PDF is also used for probability density function, so to avoid any confusion we'll always use the term cumulative distribution function and use the abbreviation CDF. The specific objectives of this module are to define the term CDF, to learn the properties of CDF, and to understand the types of random variables specified in terms of the CDFs, namely discrete, continuous, and mixed random variables. In a previous module, we had defined the term random variable as a mapping from some sample space onto the real line. Let us consider there is some sample point in the sample space, then that sample point, say small omega, gets mapped through the random variable x onto the real line as a number, as a real number. In general, a set of points in the sample space will all be mapped onto different points on the real line, forming an interval on the real line through the random variable x. So how to characterize this random variable x? The random variable x is characterized in terms of its distribution function. So let us clearly write it. How to characterize a random variable? Well, a random variable is characterized in terms of its CDF, the distribution function, or PDF, the density function, which we shall see in a later module. So how to define a CDF? Cumulative distribution function. It is defined as capital F subscript capital X in bracket small x, defined as probability of the event small omega set of sample points in the sample space such that the mapping x of omega takes values less than or equal to small x. Let us clearly write down the symbols that we have used here. This F denotes the CDF, capital X denotes the random variable, small x denotes the value that the random variable takes. This symbol, the triangle equality, is used to define the distribution function, and it is read defined as this small omega denotes the sample points for which the mapping x of omega takes values less than or equal to small x. This is capital omega denotes the sample space. For convenience, fxx in short is written as In short, this whole is written as probability of capital X less than equal to small x. We don't explicitly mention the underlying sample space and sample points, but they are understood, and we always write fxx equal to probability of capital X less than equal to small x. So this is the form that we always use. Let us look at some properties of the CDF. Properties of CDF of a random variable x. The first property, because CDF is a probability, it must follow the properties of a probability measure. So fxx being a probability must lie in the interval 0 to 1. Number 2, the CDF fx of minus infinity is equal to 0 and fx of plus infinity is equal to 1. That's very obvious, because say this is the real line and here it is minus infinity. Fx of minus infinity implies that we mean the probability that capital X takes a value less than or equal to minus infinity. It must be 0, because probability of x equal to minus infinity is 0, the basic condition that we put on a random variable. And fx of plus infinity equal to 1, because fx plus infinity simply means probability x less than equal to plus infinity, which is the entire real line, and all the sample points are mapped on some finite values on the real line, and therefore this is a certain event and the corresponding probability must be 1. The third property says that for some x1 less than equal to x2, the corresponding CDFs fx x1 must be less than equal to fx x2. This is called the non-decreasing property, or it says that the CDF is a non-decreasing function of its argument. That CDF is a non-decreasing function of its argument. We'll prove this property shortly. Another property, what is called the right continuous property. This property says that the CDF fxx is equal to fxx plus some epsilon in the limits as epsilon tends to 0, where epsilon is greater than 0. So the CDF is continuous from right. This property is particularly useful when we deal with discrete random variables, in which case, as we will see shortly, that the CDF is a staircase function. In case of continuous random variable, the left hand limit and the right hand limit are same, because the function is continuous, so we don't as such require this property. Let us now prove one of the properties. Let's prove property number 3. Proof of property 3. Okay, here we are talking about two real numbers x1 and x2, let us say this is x1 and this is x2, so that x1 is less than x2. Let us define an interval here, x less than equal to small x2. We know that these intervals correspond to some events on the original sample space. So x less than equal to x2 is an event that can be expressed as the union of two events, x less than equal to x1 and x is strictly greater than x1 and less than equal to x2. Note that x less than equal to x1 including x1 and the event from x1 up to x2 excluding x1 but including x2, these are two mutually exclusive events, and therefore when we take the probability on both sides, we can apply the additivity axiom of probability and directly write probability of x less than equal to x1 plus probability of x strictly greater than x1 and less than equal to x2. So using additivity axiom of probability. And why can we use it? Because since x less than equal to x1 and x, let me write it separately, x, since x less than equal to x1 intersection x1 less than x less than equal to x2 is phi. It's a null set because these are mutually exclusive events. Therefore, we can write from here that probability of x, or this probability of x less than equal to x2 is fx x2 equal to, this is fx x1 plus probability of x1 less than x less than equal to x2. So fx x2, which is always between 0 and 1, is equal to fx x1, which is always between 0 and 1, plus something which is always between 0 and 1. So because this term is always non-negative, it follows that fx x2 is always greater than or equal to fx x1. So that is the proof. This proof also gives an important result, which is this, that the probability of x lying in the interval x1 to x2 excluding x1 including x2 is given as fx x2 minus fx x1. So in terms of two cumulative distribution functions, we can express the probability of the random variable to take values in a certain range. So that's an important result. Let us now consider a couple of examples. Example number 1, consider a Bernoulli random variable. A Bernoulli experiment is one which has two outcomes. The corresponding random variable is called a Bernoulli random variable. So consider a digital transmission example of BPSK, binary phase shift keying with two symbols. So there are two symbols in the symbol set, minus alpha and alpha. Let us say the random variable x maps minus alpha to a number 0 and plus alpha to the number 1 on the real line. So then that makes x a Bernoulli random variable. Let us say the probability of x taking the value 0, or in other words the probability of the symbol minus alpha to be transmitted is equal to small p. Then the probability of the transmission of symbol alpha, which is equivalent to probability of x equal to 1, will be 1 minus p. We can call it as q. Then the CDF of x will take the form, so this is small x, and let us now make the CDF. Suppose this is 0.0 and this is 0.1. So when when small x is less than 0, so fx will be 0. When small x is equal to 0, then fxx is the probability small x, capital X less than equal to small x. So when small x is equal to 0, so probability of x less than equal to small x is p. So it takes a value p, this is p, and it remains p as long as x is less than 1. The moment x is equal to 1, then this becomes probability capital X less than equal to 1, which includes 0 and 1 both. The probability of 1 is q, 1 minus p, so it is 1 minus p, this is 1 minus p, so 1 minus p plus p, so this whole is actually 1, which a CDF should be. So this is 1, and then it remains 1. So this is the CDF of a Bernoulli random variable. As we can see that the shape of this CDF is a staircase shape. The function has the form of a staircase, and this is a typical characteristic of what we call a discrete random variable. So this is an example of a discrete random variable, because here the CDF is a staircase function. Let us take another example of what we call a uniform random variable. As we shall discuss in detail in a later module, a uniform random variable has a CDF which is a straight line from 0 to 1 in some interval, say 0 to t, this is 1. So this is, as you can see, there is no discontinuity, there is no jump here. This CDF is that of a continuous random variable, in short a CRV. There is no discontinuity here. To conclude, let us write down some examples of discrete random variables. As we shall see, Bernoulli we have seen. So Bernoulli random variable, binomial random variable, Poisson random variable, The examples of continuous random variables include a uniform random variable, Gaussian, one of the most important random variables, also called normal random variable, exponential random variable, Rayleigh random variable, and there are many such random variables which are very important in studying various branches of engineering, especially communications engineering. There is yet another variant of random variable possible, in which the CDF takes the form of a discontinuous function plus a continuous function. For instance, a CDF which has a staircase part and which also has a continuous part. So such a random variable, such a CDF characterizes what we call a mixed random variable. So this is a mixed random variable. So in this module we learn how to characterize a random variable. One way to characterize a random variable is to define its CDF. We looked at the properties of CDF. We also proved one of the properties of CDF, and we looked at different types of random variables as they are specified in terms of their CDFs. So that's all for this module. This is Kamlesh Gupta signing off. Goodbye.